welcome to the third day of our ALGA conference. So let me introduce Maria Braz Amoros. It's a pleasure to have her here. She's from the University of Rovira in Virgili, and she's going to talk about numerical semigroups and algebraic geometry codes.
Okay, thanks for the presentation, and thanks to the organizers for inviting me to give this talk. It's a pleasure to be in such a nice place. And I'll talk about some of the topics in which I've been working for a long time. I'll talk about numerical semigroups and then how some things on numerical semigroups can be applied to coding theory. The first part of the talk will be about theory of numerical semigroups. And then in the second part, I will combine things of numerical semigroups and the applications they have in coding theory. For instance, the last third points, I will talk about the new sequence and the tau sequence that I introduced in the first part and explain how they apply to coding theory. We will use a bound using generators of a semigroup. Then we will see how this applies to coding theory. And then we will see also how semigroup ideals apply to coding theory. OK, so let's start by the definition. Probably many of you already know the definition of a numerical semigroup. It's a subset of the non-negative integers, which contains 0, is closed under addition, and its complement in the set of non-negative integers is finite. The number of elements in this complement is what we call the genus of the semigroup. And here we have an example, 0, 4, 5, 8, 9, 10, and everything from 12 on. This is a numerical semigroup because every time we add two numbers here, we obtain another number here. 0 is in the set, and also the number of elements that is not here is finite. Then the elements that are not in the semigroup are in fact the elements that have a name. They are called gaps. And the elements which are in the set are the ones that have no name, so we call them the elements that are not the elements that already have a name. So this is kind of a joke in mathematics, but here we have a name for the gaps. And the non-gaps are the elements of the semigroup. OK, then the third condition, the fact that the complement is finite, implies that there exists a Frobenius number. The Frobenius number is the largest gap. And there exists a conductor, which is the largest gap plus 1. This means that this is an element of the semigroup, and that everything from this element on is also in the semigroup. As an example, we can think the amount of money that can be taken away from a cash point. We can always take nothing, so 0 is in the set. And if I can take away, for instance, 20 and 50, then I can take away 20 plus 50, which is 70. And every different two amounts that I can take away from the cash point, I can also take away the sum of the two amounts. Then if for the complement to be finite, we need to divide everything by 10. If all the currency amounts are multiples of 10. In this case, the semigroup would be 0, 2, and everything from 4 on. Another nice example comes from music. When we play an acoustic instrument, every time that we play a note, there are a bunch of other tones that go together with the note that we are playing. Those are called the overtones of the fundamental tone. And for instance, if we played a C or a Do, the overtones that we would get are the notes that we have written there. if we divide the octave into 12 equal semitones, then we can, I don't know if you see the colors, but there's some of the keys are in pink, and these keys would correspond to the fundamental and the overtones. If we count what interval is there between the fundamental and each of the overtones, the differences are 0 from the fundamental to itself, 12 from the fundamental to the first overtone, 19 to the second overtone, and so on. And we obtain again a numerical semigroup. And the reason here is physical. Because, the thing is that the overtones of an overtone must be overtones of the fundamental tone. And this is why this is closed under addition. And the complement is finite because our octave is divided into a finite number of semitones. Okay. And another outstanding example is the example of Weierstrass semigroups. We suppose we have a curve which is projective, non-singular, and geometrically irreducible. We distinguish a rational point in the curve and consider the ring of functions on the curve having poles only at this distinguished point P. Then we consider the set lambda of all pole orders of these functions that have only poles in P. Again, this set satisfies that 0 is in the set. The sum of any two things in the set is, again, another thing in the set. And the number of elements which are not in lambda is exactly the genus of the curve, and so it is finite. In fact, this is the reason for which we call genus the number of gaps of a numerical semigroup. As an example of Weierstrass semigroup, we can consider the Hermitian curve over, in fact, this is over F16, not over F4, with this equation. This curve has only one point at infinity, and the Weierstrass semigroup corresponding to this point at infinity would be the red numbers we have on the right, 0, 4, 5, 8, 9, 10, 12, 13. In fact, there's something very important of a numerical semigroup, which is the enumeration. The fact that the numerical semigroup is included in the non-negative integers implies that there's a unique increasing bijective map from the positive integers, from the non-negative integers to the semigroup. So we can call the first element lambda 0, the second element lambda 1, lambda 2, lambda 3, and so on. For instance, in the semigroup of the harmonics, lambda 0 would be 0, lambda 1 would be 12, lambda 2 would be 19, and so on. Okay, and finally, the generators of a numerical semigroup are those elements that cannot be obtained as a sum of two smaller elements. In the case of the cache point, for instance, 6 can be obtained as 3 times 2, 7 can be obtained as 2 plus 5. Those are non-generators. The generators are just 2 and 5 because there's no way to obtain them as a sum of smaller things. Now, we'll introduce these two elements, the new sequence and the tau sequence of a numerical semigroup. And the new sequence is defined as follows. Suppose we have a numerical semigroup enumerated by these lambdas. Lambda 0 is the smallest one, lambda 1 the next one, lambda 2, and so on. We call nu I the number of elements in the semigroup that can be subtracted to lambda I. So every lambda j such that lambda I minus lambda j is in the semigroup, I will count it, and the total number of these lambda j's will be this nu I. For instance, if we go back to the Hermitian curve example, the the first element is 0. In this case, there's only one element which I can subtract to 0, which is itself. And so the nu in this case is 1. In here on the right, I wrote the number of elements that can be subtracted to each non-gap. For instance, if we take here, let's see, sorry. Here, yeah. Let's say lambda 7 is 13. And there are 6 numbers that can be subtracted to 13 and still obtain something in the numerical semigroup. And the 6 numbers are those here, 0, 4, 5, 8, 9, and 13. This gives us a sequence, the sequence nu sub I, which is associated to a numerical semigroup. Similarly, we have this other sequence, which is the tau sequence. And in this case, we consider tau E. For tau E, we look at lambda I. Sorry, we consider tau I. Then we look at lambda I and see from all pairs of numbers which add lambda I, from all those pairs, we take the one in which the 2 elements are closer. Here, I draw again the same example as before, but I put in red the pairs of numbers whose sum is the non-gap, but in such a way that the two non-gaps are closer. Then from those 2 non-gaps which are closer, we take the index of the smaller one, and this gives us tau. Again, if we go here to here, again with lambda 7, we have all these numbers are elements that we can subtract to 7, and in particular, we can subtract to lambda 7, which is 13. 5 and 8 are the ones which are closer, and we look at lambda 5. Sorry, 5 is lambda 2. You see, 5 is lambda 2. So in this case, tau is 2. Tau is the index of the smallest one of these 2 elements whose sum is the non-gap. Okay. Now, these sequences have an interesting property, is that if you have the new sequence of a numerical semigroup, it uniquely determines the semigroup. And the same happens with the tau sequence. But on the same time, you need the infinite sequence, because otherwise, for every finite part of these sequences, you have infinitely many numerical semigroups whose sequences start with these finite numbers. Sorry? No. With just one of them, you obtain the numerical semigroup. If you have all new values, you have the numerical semigroup. If you have all tau values, then you also get the numerical semigroup. Okay. So we are ready to introduce 1-point AG codes. First, a reminder, a linear code of length n over fq is a vector subspace of this finite field fq to the n. The dimension of the code is the dimension of the linear space. And we will be interested in the dual of a code. The dual of a code can be understood as the orthogonal complement of this code. That is, if our code is C, then we take all words such that multiplied by any word of C is 0. And this will be the dual code of a code. And the parity check matrix of a code will be a matrix whose rows are the generators of the dual code. And this matrix is used to compute the syndromes, and the syndromes are used to correct errors. Okay. Now, in the particular case of 1.8G codes, we have, as before, a projective curve without singularities and geometrically irreducible. We distinguish a point, P. We consider the functions that have poles only at P. We consider its Weierstrass semigroup, lambda, and we enumerate its elements by lambda 0, lambda 1, and so on. And we take a set of functions such that, and they are enumerated f0, f1, and so on, such that f0 has a pole order of order lambda 0 in P, and so on. Then we consider a set of n rational points different from P, and we consider this evaluation map. The evaluation map sends every function with poles only at P to its evaluation to P1, P2, up to Pn. And then standard codes are defined as this code here. A standard code would be the dual. Here we have a dual. So it's the dual of all the code words which are obtained as the evaluation of functions having only poles of order at most lambda I at P. And this is equivalent to, if we think of Riemann-Roch space, this would be the same as evaluating all functions in the Riemann-Roch space associated to lambda I P. This is the classical approach. Here I want to talk about another approach, which is, instead of taking here the evaluation of f0, f1, f2, up to a given number, we just evaluate functions with maybe maybe we evaluate f0, f4, and f7. They don't need to be all in a row. And for this reason, we need this subset R. In the standard case, this I is an index, and this would give us the number of rows that we have in our parity check matrix. And here, this is a set. It's a set of indices, and the number of indices will be the number of rows in the parity check matrix. As an example, we continue with the Hermitian curve. The Hermitian curve has one point at infinity, which we call P. This P will be the point at infinity. And this has 64 points, but 64 affine points. I just wrote the first ones here. And in this case, the functions having these pole orders in the numerical semigroup would be those ones here. F0 has order lambda 0, F1 has order lambda 1, F2 has order lambda 2, and so on. So evaluating these functions, this is a matrix in which I put in the first row the evaluation of F0, which is the evaluation of 1. This is why everything is 1 in the first row. In the second row, this is the evaluation of X. And this is why in this first row, I have the X's of all these points here. In the next row, I have the Y's. And this is just because I keep increasing the order of these functions and evaluate every time all the points in these functions. Okay, then the classical paradigm would be the first case in which I just consider all rows of this parity check matrix up to a given number. And instead, in the case in which I have a subset of indices, I take some particular rows in the parity check matrix, but they not need to be all in a row. I mean, they don't need to be all subsequent rows. Okay, now we'll see why we got interested in this, this rare thing of not taking all indices in a row. And the thing comes from error correction. First of all, we need to define what are generically distributed points. We say that a set of t points is generically distributed if there's no element with order at most lambda t, which vanishes in all the points, okay? I have some examples to make it more clear. For instance, in the Hermitian case, as before, two generic points. Generic points would be almost all points. Non-generic points are the particular cases. And so now, in the example, I will look at the particular cases, the distributions of points which are non-generic. If we have 2 points, they are non-generically distributed if they are in a horizontal line. We can already see that this is rare. If we take 2 points at random, they will probably not be generic. They will probably not be in a horizontal line, so they will, with high probability, be generically distributed. If we have 3 points, they are non-generically distributed if they are collinear in any kind of line. So again, if we take 3 points at random, the most likely to happen is that they are not collinear, and so they will, in general, be generically distributed. In the case of 4 points, they will be non-generically distributed if they all belong to one parabola of this shape here. So now we can define generic errors, and generic errors will be these error words in which the error positions correspond to points which are generically distributed. In our codes, every coordinate of every word corresponds to a point because we are evaluating functions in points. So every coordinate is evaluating different functions in a given point. So we can label the positions in a word by the points at which we evaluate in this position. So an error will be generic if the points corresponding to the non-zero positions are generically distributed. Then it can be proved, although it's quite intuitive, that generic errors can be a very large proportion of all possible errors of the same weight. So we will focus on the decoding algorithm, how the decoding algorithm works if we just want to correct these generic errors and accept not correcting errors which are non-generic. By restricting the errors to be corrected to generic errors, one has weaker decoding requirements and still can correct lots of errors because we are assuming that almost all errors are generic. Okay, so we have one first theorem by Feng and Araujo. They proved that, in fact, they constructed their algorithm, and their algorithm works if the set of parity checks, this set R, contains all i's such that nu I is more than 2t plus 1. On the other hand, if we only want to correct generic errors, what we need in our parity checks is to have all indices I for which tau I is less than t. And this is how the nu sequences and the tau sequences that I presented at the beginning appear here. Then, we need to keep these 2 conditions in mind. For correcting any kind of errors, we need all parity checks with nu I is more than 2t plus 1. And for correcting just generic errors, we need to have all parity checks for which tau I is more than t. So now we can define this R tilde. This will be the set of parity checks that we need to correct any error of length t. And without the tilde, it would be the corresponding standard code. Standard code means taking all rows up to a given number. For instance, in the case of the Hermitian curve, we have, again, the set of, here, set of nu i's. We need to take, for correcting, and we suppose we want to correct 2 errors. For correcting 2 errors, we need to have, oh, there's an error here. This says lambda I, and it should be nu I. We need to take all indices I for which nu I is smaller than 5. Here we have nus, and we need to take all rows for which nu is smaller than 5. These are the red ones. So our parity check matrix will be this one, corresponding to the rows, to the red whose rows correspond to these red numbers here. And we can take away these two rows in the parity check matrix. These 2 rows make the dimension smaller, but they don't contribute to correction. So we don't need them, and we improve the dimension of the code and still keep the same correction capability. But if we want still to work on standard codes, then we will need to have all rows up to catching up this 4 here. So we will need all rows up to this here. Okay. On the other hand, if we restrict our expectance to correct just generic errors, then as parity checks, we will need to consider all rows corresponding to this condition here, tau I is smaller than t. And then again, we can also consider the standard version, which will be all indices up to the maximum of this here. We call, when we restrict to generic errors, then we add this star here. We put y tilde when the set doesn't need to correspond to a standard code. There's no tilde if the code is standard, and we put this star when we restrict to generic errors. So in this case, again with the previous example, here I draw the values of tau, and in this case, okay. Before it had to say nu sub I, and now I have nu sub I, and it should be tau sub I. Okay, this is tau sub I should be smaller than 2. We have here the values of tau, and so we only need those the rows corresponding to these red numbers, which are the ones for which tau is smaller than 2. In this case, we would have only 6 rows. We will only need 6 rows, and if we want the standard code, then we have 7 rows. Before we had 8 and 10, so we keep improving by just allowing to have some correction errors when errors are non-generic. This is a picture of the redundancies of all these codes. In the case of the Hermitian over F49, and we can see that always the worst version is having standard codes. Here, blue would be standard code correcting any kind of error. Then we have these redundancies which are high, which means the dimension is small. And the best option is when we restrict to generic errors and taking only the specific rows that we need. And this is when we get the red points. So there are interesting interesting problems in numerical semigroups related to this scenario. For instance, one problem is studying the increasingness of nu, or the increasingness of tau. This would tell us if there's a difference between standard codes and non-standard codes, because the standard code is different than the code defined by a set, only if the sequence nu or the sequence tau is decreasing at some point. So the increasingness of nu will allow us to compare these two sets. The increasingness of tau will allow us to compare standard codes correcting generic errors than codes just correcting generic errors. And finally, comparing nu and tau will allow us to analyze the improvement of correcting only generic errors. There are some results like this. There are a bunch of results here. I just put some. But for instance, the unique semigroups for which nu is non-decreasing are ordinary semigroups. And by ordinary semigroups, we mean the semigroups which contain 0 and everything from a constant. Those are ordinary semigroups. Those are the unique semigroups for which nu and tau are non-decreasing. And so these are the unique semigroups for which there's no improvement, there's no difference in taking standard codes or non-standard codes. On the other hand, we always have that tau I is larger than or equal to this nu I minus 1 over 2. They are equal for if I is large enough. And they are equal at every index, even only if the related semigroup is ARF. And ARF semigroups are, I didn't define them here for not having so many slides, but they are a very particular case of semigroups in which for every time you have 3 elements in the semigroup, you can subtract the smallest one to the sum of the other 2. And we have some curves whose semigroup is ARF. For instance, I think some of the towers of Garcia's Thyssen, some of the towers, the semigroups there were ARF. So ARF semigroups appear, but it's not that they are the most common semigroups. So as a corollary, correcting only generic errors is always better than correcting everything, as we would expect. There's no difference, even only if the associated numerical semigroup is ARF. And furthermore, if the number of errors is large, there's also no difference. These differences are evident when the number of errors we want to correct is small. Okay. Now, another parameter there are other parameters on codes which can be parameterized by numerical semigroups. There's a very important one, which is the minimum distance, but I had to choose what to explain because I thought I wouldn't have time to explain everything. So for the minimum distance, I will need to come again and give another talk. I will not talk about minimum distance today. But I will talk about the length of these codes. And the length of these codes, by the way they are defined, has to do with the number of points of a curve. And we have this first bound by Serre, Hasse, and Weil, which takes into consideration only the genus of the curve. Somehow this is related to Weierstrass semigroups, because the Weierstrass semigroups have genus G. So we can think of this bound as related to semigroups. But it uses just a very small thing of a semigroup, which is the genus. We have this other bound, which takes into consideration the whole semigroup. And this bound is better than the Serre-Hasse-Weil in many cases, not always. Although it's obviously more complicated to compute. So there's some work to do here in the computation of this bound. And finally, I want to talk about semigroup ideals and the relationship with isometry dual sequences of codes. Although in next talk, we will already hear about these sequences. First of all, the part on ideals. If lambda is a numerical semigroup of genus G and Frobenius number F, then we have this bound for F. F is at most twice the genus minus 1. And this is the proof of this is very easy, just using this pigeonhole principle. Ideal of a numerical semigroup is a subset, as usual. That you can add the subset to the ideal and still obtain something which is in the ideal. Now, we are interested in which is the maximum. As in the same way we have the maximum gap of a numerical semigroup, we are interested in which is the maximum gap of an ideal. We call it also the Frobenius number of the ideal. And we could prove that it depends on what we call the difference of the ideal. The difference of the ideal would be the number of elements in the semigroup which don't belong to the ideal. And in this case, we have this bound. The Frobenius number of an ideal is at most 2G minus 1 as before, plus this difference. This bound is sharp in the sense that there exist ideals which attain this bound, and these ideals are called maximum sparse ideal. These maximum sparse ideals have been applied, for instance, in the computation of generalized Hamming weights. I don't have time here to explain it. But we will see now how these ideals relate to these isometry dual sequences of codes. Here we will say that two codes are x isometric for a fixed x with non-zero coordinates if the elements of one code can be obtained from the elements of the other code just multiplying coordinate by coordinate by the constant vector x. Suppose we have a sequence of codes, each one included in the next one. The dual codes satisfy the opposite inclusions. And we are interested in the case in which there exists a constant vector x such that each Ci is x isometric to the corresponding dual of C sub n minus I. These sequences have been studied in the literature in last years with applications to quantum computation and to other things, and also to the computation of the minimum distance. And we will look at these sequences when there's in the case of one-point codes, because for one-point codes, there's a natural inclusion of codes. And the natural inclusion of codes comes from these standard codes that we saw before. In standard codes, every time we can add a row and add another row and add another row, and we get these sequences of codes. Let's call W the Weierstrass semigroup of one distinguished point in a curve. And we call W star the indices I for which there's a jump in the codes associated to lambda I. So the thing is that we can have a jump in the Riemann-Roch spaces L, but this doesn't mean that we have a jump in the codes. So W keeps the jumps of the Riemann-Roch spaces, while W star keeps the jumps on the corresponding codes. Then W minus W star it can be proved that this is an ideal of W. We already know that W is a semigroup. Then W minus W star is an ideal of W. This was proved by Gail, Munuera, Ruano, Torres without any reference to ideals, but it seems to be a theory which is very nicely fit in the theory of ideals, and especially because we can characterize in which cases the sequence of codes satisfies the isometry dwarf condition, and this is exactly when the ideal given by W and W star is maximum sparse. And with this, I finish some of the things I wanted to explain today.